webinar. We're just going to give it a minute or 2 minutes and give everybody a chance to join. And then we'll kick it off with a live demo and then some deep dive into the protocol. Kali, how are you doing today?
I'm doing well, thank you. Hopefully, my connection holds up. I'm in the middle of a blizzard right now up here in Canada, and that sometimes messes with the connection. So we'll see if that holds.
All right. Well, good luck with that. Yeah.
Yeah.
On all accounts. Yeah.
Yeah. It's cold up here today. -20 Celsius.
Oh wow. Okay. So since I basically spent the last 15 years in California, I don't know what that feels like, but it does sound very unpleasant.
Yeah.
When I was still in Bavaria, I knew what that feels like, but I forgot.
Yeah, it's easy to forget. All it takes is a summer season, and then it's like
It's very true.
I'm outside of Edmonton, so it's north of Calgary. You're probably familiar with Calgary, in Alberta. Yep, lots of agriculture.
So, all right, but no agriculture today. Today it's all technology. So, by the way, for anybody who is currently joining, welcome to the Resonate webinar. So, if you have not done so yet, go join our Discord at resonatehq.io/Discord. We of course chat about Resonate and distributed async await, but we also chat about distributed systems in general. For example, deterministic simulation testing. So lots of interesting stuff in and around distributed systems. So now 2 minutes in, I'd say we kick it off. So today on the agenda, Kali is gonna give us a live demo of the Python SDK together with the Resonate server. And it's like, I encourage you pay close attention to the resulting developer experience, because the developer experience for Resonate, right? The developer experience is in the center of what we do. And we characterize our developer experience as being dead simple. And that is true for all of Resonate, right? So it's supposed to be dead simple to understand, dead simple to develop with, and dead simple to operate. And in the live demo, you're going to see how our vision of like dead simple development manifests. So then I'd say, Kali, like take it away and walk us through the demo.
Awesome. Okay, cool. Thanks, Dominic. One point just to build on what Dominic was saying about joining our Discord channel. One of our recent changes that we made was we created a dedicated Resonate engineering channel, and we've definitely made an effort to move all of the engineering conversation to that channel. So yeah, if you have any interest in following along with the development and the decisions and what goes into it, please join us there and feel free to contribute, ask questions. We love it. So I'm going to switch into demo mode here. And to do that, I will share my screen. So it looks like we're good here.
Yeah.
A demonstration will be of this application. So it's a summarization app which downloads some content from the internet. You give it a URL, it will download the content, basically do a web scrape, and then a llama will summarize the content and give that back to us. What is particularly cool about this app is that we've got the summarization step in a loop. and we are going to confirm or reject the summarization. There's a lot of agents I see out there, or agent flows. I've been seeing basic ones where the AI does something, and then you have to have a manual, like a human, basically verify the work that the LLM has done. So this replicates that experience where an AI agent has done something, and you want to verify how it's done. And if it doesn't do exactly what you want it to do, you can reject that and have it repeat the step to see if it can do better. So that is in a loop here, and the uh, the developer experience, we think, is really, as Dominic likes to say, dead simple, because you're basically just blocking here, right? You're waiting on a confirmation, and if it and you can actually pass data into this. Um, I think the uniqueness is that you can push the data in rather than pull from the function. So normally these functions would be pulling data in by calling, right? But because it's awaiting on a promise, the resolution of the promise contains data, and that gets pushed back into the function, and can update how it decides to move forward. The other thing I'm going to call out before we do this is that um, this application is one you can build yourself if you follow along with our new Getting Started tutorial, which we released this week. So you can go to our doc site, go to the Python quick start, and follow along to all the way part number 5, which will then get you to this exact application that I'm demonstrating right now. We'll build out to this example. It is a pretty comprehensive tutorial in that, a lot of Getting Started tutorials kind of focus on just the bare minimum, which you can do. So every section will leave you with a working application. Um, this Getting Started tutorial will actually walk you through several of the major, you know, pieces of functionality that you get with Resonate that is typically like challenging to do on by yourself, or just like to get going, including crash recovery, fan in, fan out, human in the loop. And then at the very beginning, like it's really easy to get going because um, you just import the SDK to your project, and you can get going using it for some basic stuff like automatic retries, and then start using the server and get going from there. So anyways, point is, this tutorial will get you the same application that I'm demoing right now. And if you do end up diving into this, we would love your feedback. Please let us know. Come join our Discord. Tell us what you think. All feedback is welcome. I will say there's one caveat in that we just this morning discovered that the brew install step is getting an older version. So if you do get to this step right now, just clone the repository, check out 0.7 version of the server, and run that, and using Go, and you'll be good to go there. But our team is currently working on it, so by the end of today, I expect that this will work just fine. Okay, so let's get to the demo. First, I'm going to run our gateway, which has 2 endpoints here. The initial the first endpoint we're going to hit is the summarize, and then later we'll hit the confirm endpoint. So I'm going to run this gateway. Oh, look at that. Typical. I need to also run the server. Awesome. So let's try that again. Run the gateway, and then we'll run our application. and I'm going to have this app summarize the Resonate HQ website. This email doesn't really get used. What we're mimicking or mocking out is that you would receive the summarization in email with a link to confirm or reject, and then the process would either finish or continue on from there. So let's go ahead and send that in. And the first step is to download the content directly to the application node. And we'll take a quick look at the code in just a second, because there's some really cool simplicity there. All right, so we've got some summarization returned from Olama, and let's say that we're not super happy with this summarization. We think it can do better a second time, so we're going to reject that, and it will kick it off again. This time we'll confirm it. Say, okay, that looks good, let's say, and then the workflow completes. Awesome. Let's see if we got some new people joining in to our chat. Okay, so let's take a quick look at the code again, because a couple things we want to point out with what you just witnessed here. The first is that we're not going to assume that the content that we're scraping is small enough to be stored into a durable promise. That's important. So what that means is the content will actually get downloaded to the application node. That means that if this were to fail, right, if this were to fail halfway through, and recovery happens and gets picked back up on another application node, we would want to re-download that content before the summarization happens. And that's made really simple with this option durable equals false. You might argue, well, why not just put that in a regular function? And well, by using Resonate to call this function, you still get the automatic retries. So if it fails downloading, then that will automatically retry until the download succeeds. But if the actual application node crashes and gets brought back up on another application node, then Resonate will know to actually rerun that function there and download the content, so that the rest of this will work on another application node. The other thing I'd like to call out here is what we've done is we've, in order to enable the human in the loop part, is we've manually created a promise. When I say manually, basically we do a remote function invocation with this call here, which creates a durable promise in the server, not associated with any function execution. So it's a durable promise there. We get the promise here with its metadata, which includes its ID. So then we can put that in the link that we send in the email, so that when the user clicks on the link and it goes to the gateway again, here, we can actually extract that ID from the URL, pass it back to Resonate, and resolve that promise, which the entire workflow blocks on the resolution of that promise right here. And we get that data that we pass with it, and then continues on. And obviously that the data determines, if it's true or false, whether or not we stay in this loop or we break out of it. Last time last webinar, we did do a demonstration on fan out and fan in as well, and crash recovery. And this app will do that as well. So, see, I can do a couple more. Do this, and we can come up with a couple more. What's a few websites we want to summarize here off the top of your head?
Kubernetes.io.
Kubernetes.io. Make sure I spell this right. Kubernetes.io. That looks right?
Let me see if that's actually the right website, but I think it is.
We're going to try it. See if my error handling works. Yeah. Okay. That worked. So that immediately got picked up by the second application node. So while that's processing, what else do we got?
Let me see. Still,
you can think of
Kafka. Hold on. We do kafka.apache.org. I'll send you that in the chat.
Kafka.apache.org. Oh, that one's no good.
I send you the link in the chat. Promotion.
Well, that'll keep going until the promise is resolved. Not good handling there. In the chat. Hold on, let me get to the chat here. Right. Which chat did you send it in?
The Riverside.
I'm not seeing it. I can go
Kafka.apache.org.
I guess we'll just go. No, I'm taking all over the place. There we go. Going off the rails. I think it's just this, yeah?
Yes.
There we go. All right. So let's say let's say this node crashes because there's a lot of errors happening. Then it will pick back up over here. Even though that URL is bad. So you can see I have some work to do and some error handling here if you don't get a good URL.
If you get a 404 and you have a reliable process, then you are actually in trouble. Yeah.
Yeah.
Then you have to wait until the timeout hits you.
Yeah. Yeah. Unfortunately, there's that. But we've got these, we can stop some of these here. We confirm that. So that workflow will complete. And then I better stop this or it's going to keep going. Okay, cool. So, I mean, you get the gist of it there. It does look like I need to add some error handling if you're not dealing with a perfect URL. But that would, I didn't want to spend too much time on adding too much logic here that might take away from some of the core value propositions that we're trying to get across. But I think you get the point. So, curious if there's any questions. Can you throw a non-retriable error of some sort on 404, or do all errors retry? That correct. So
yes,
you can. Yes, exactly. So if I had specified no retry on 404, that's exactly what we could do on this. Is a great question. Then it just we wouldn't retry at all. Correct. So, and you can actually do that in options. So I think which one is it? Download right here. Yes, I think we could actually. I don't know if Tomas is on the call, but you could probably do something like this: retry policy equals, and then add in non-retriable error. I think it is non-retriable, something like that. I have to check out the SDK reference to be sure the exact fields there, but you can specify non-retriable, and then it just won't. Yeah, you just won't retry, and the whole thing would. I think that would cause the workflow to then, well, not the workflow, but the promise would then hit a failed or rejected status. Correct me.
Rejected. Yes. Mm-hmm.
Yeah. So you'd have that. Yep.
Whereas you obviously still have to handle what you want to do after that. But yes, so you can fine grain specify if you want the retry loop to retry a function that fails or throws an exception. And if you don't, then the promise is rejected. But again, then the question is, what do you want to do next? So there is still a chance to add more business logic to that. Whereas in this case, we will probably just like return, right? Because then it's like, all right, we tried, we can't even download. So we're basically done with this particular workflow. But of course, you can still catch that exception yourself on an application level and then decide what to do from there.
It's actually a really good call out, and probably something we'll add to this app and add to the tutorial now that I'm thinking about it, because that's a really very relevant thing that we would want to do here, actually. Yeah. And didn't notice it until I added and tried a URL that didn't work.
Right. It is actually it is a very nice application for that because it's like, yeah, exactly. So it's very simple to basically just pick up on the 404 and then in the tutorial, right, and say it's like, okay, this is how you can configure it as non-retriable, and then this is what we are going to do afterwards. There's also an very interesting side effect of this durable computing idea, right? Of this idea where you have processes that cannot crash, where in this case you can argue I wanted it to crash because then it would basically not do anything, right? But this quote unquote crash-proof architecture, right? In this situation, it will not crash. Now, will it get in your way? Not necessarily. Will it consume resources? Yes, because it keeps on going.
Yeah. Tristan asks, can you explain the difference between LFC and RFI, and when do you use each? Yeah, absolutely. Okay, I'll take a quick stab, and then Dominic's going to probably correct me and refine on what I'm saying. We have remote function invocations and local function invocations, and then RFC, which is a remote function call, is just syntax sugar on top of RFI, basically, which immediately awaits for the resolution of the promise. And then same thing with LFC, that's syntax sugar on LFI. So you could make a invocation, get the promise, and then not do any, right? You're not waiting on it. Or you do an LFC, which means you're waiting on the resolution of the promise right there and then. Here, so this gateway is technically an application node, a Resonate application node, because we've initialized an instance of Resonate, we've connected to the server, and this function here will in the future, you should be able to do RFIs directly from the top level Resonate. At the moment, you have to do a local function call to another function that then can do an RFI. But basically, you have two options. You can do a local function invocation or a remote. Local will call a local function on this application node. So if we go over to the app here, all these are local function calls. The rest of this stuff is defined here, right? So these would all get invoked and execute on the same application node. Whereas this one makes a remote, and that will cause a task to get created on the server, which then could mean that, right? It means that basically you're distributing that that execution to some other place. It could execute, depending on if the code is here, it could execute on this application node or another one, but basically you're not controlling, you don't necessarily control that at that point. I do have a diagram actually that kind of illustrates the difference. Let's see if I can get that up real quick. Yeah, Dominic, what do you feel free to jump in and clarify.
I have some parts of that in the presentation that I am that I have queued up. So if you want, I can take over from here.
Sure. Real quick, I did find the diagram. This is pretty heavy. But the main difference with the RFI from this diagram we can see is that a task will get created as well as a promise versus just a promise getting created and then being associated with that invocation. But this will probably make more sense after Dominic dives into his chat. We can use this to help answer questions if we need to. Okay, so I'm going to stop sharing and then. Oh, another question, although no need to answer. Why have you decided to use yield here versus async await? Great question. That's actually a great question. But I'll stop sharing and.
I can take that on as well.
Awesome.
So. All right, cool. So Kali showed us the source code that you write. So basically showed us the distributed on concurrent programming model, right? That is how we express the concurrent and distributed structure of our application. And then for the rest, we dive into the execution model, right? So the distributed and concurrent execution model. How do you actually execute that concurrent and distributed structure of your application? And so here is the source code again of the download and summarize, the main one, right? So first, we locally download the file, and then we also locally create the summary. Then we create a durable promise, but we do not await it. Then we we locally send the email and then we await the promise. So here you see the difference between the local function invocation and the remote function invocation. So first off, LFI, RFI, LFC, and RFC are our lowest level, functions that we have in the system, and that basically demonstrates the very core flow. So a function can yield an invocation, and then it will receive a promise, and it can yield a promise, and then it will receive a value. So yielding a promise is basically then awaiting on that promise. And a core idea of Resonate is that you, as a software engineer, you make the call. Should something happen locally, that means it runs here, right? Or should something happen remotely, which means it can run here, but it can also run somewhere else. For example, fan in, fan out. That is a very important distinction. So for us, location transparency is by no means that you shouldn't know where something runs. If you look at this source code in particular, we are downloading a file to this node, right? Therefore, we are calling summarize also locally. It would not help us if we let the system decide where to run summarize, right? Summarize must run where we just downloaded the file, right? So that for me, it is not the right interpretation for location transparency. If we say, well, location transparency mean it can run here or somewhere else. No, that is a very important decision that is in your hands as a developer. You can say run it here, or you can say run it somewhere else. For us, location transparency means if you run it somewhere else, it basically doesn't matter where you run it. Yeah? It doesn't matter if you run it on node 1, on node 2, on node 3, or node 4, we can just represent it via a promise and you can just wait on it, right? That is the interpretation of location transparency. Now, that also means that we have a delineation in our asynchronous call graph, right? So async await spans a call graph. It's not a call stack, since you can start multiple things, unlike sync, right? You can start multiple things at the same time, therefore it's a call graph. But our call graph is basically also delineated by machine boundaries. Every time we hit the RFI, we have a potential machine boundary. So now we are only looking at the partitions of the call graph that happen on other machines, right? So we basically fold everything that we call locally into the same part of the call graph and only look at the pieces that are distributed. And from here, we will see this partitioning of our call graphs. So we have download and summarize, and we have an external process. Now, human in the loop is actually also super cool to demonstrate that durable promises are not just primitive for coordination. They're also primitive for integration. Because anything that can be represented as a durable promise, basically any process, anything that has a definite beginning and a definite end, can be represented as a durable promise, and then the SDK can just await it, right? In this case, we're actually not waiting on another function execution, we're waiting on a human execution, so to say. So that is a human in the loop step. But from the point of the SDK, there's no difference. From the point of the SDK awaited the promise, and whether that promise is fulfilled by yet another resonate function, by yet another completely different technology, like for example Spark or an Apache workflow, if they are exposed via durable promises, or a human in the loop, there is no difference here. So now you can already see the core interaction between the individual parts of the call graph. That is first basically an invocation, right? So the download and summarize invokes something. That was the first line, the RFI line. Now, the second one is an await, right? That is a primitive for coordination. That doesn't matter if it's local or remote. Await is a primitive for coordination, meaning that the awaiting execution is blocked until the promise is resolved. And that is basically what then makes the awaiting execution resume, able to take the next step. And the contribution of Resonate is that we can not only express the temporal dependencies, the concurrency, that's something that's inherent to async await. The contribution is that we can actually do so across machine boundaries. So now we can also express the spatial dependencies, the distribution. That's when you can say LFI, and that's when you can say RFI, right? That is like you decide not only on the concurrent structure of your application, you also decide on the distributed structure of your application. And the reason we went with yield instead of async await is that with yield, you get very, very fine-grained control about your execution, right? Because you have a piece of user code that whenever your code, basically a piece of user code, whenever your code hits that yield point, it returns control to our framework, to our Resonate SDK, while still keeping the state. And that's always fantastic developer experience there, because it allows you to write code linearly, but we can execute it in an event-driven manner. Now, can you argue that you can fold that into the async await machinery? That depends a bit on the language. So, for example, TypeScript and JavaScript, they do not expose lots of hooks into their machinery. So very, very difficult. Python and its event loop exposes more hooks into its machinery, but they still take over a lot of that functionality, right? So at some point, you may be fighting the Python event loop more than your basically its partner in crime. So that's why we decided to go with yield. Now, it is yield heavy because you yield an invocation and receive a promise, and then you yield the promise and you receive the value. There is a potential of optimization in the sense of getting rid of some of these yield statements. However, that slightly alters the semantic of the code. Whether that actually matters or doesn't matter is something we need to figure out in the future. However, right now we go very, very low level in order to have very fine-grained control and really get the kinks of that, iron out the kinks of that programming model and get that programming model just right. So yeah, to reiterate the core interaction here is an async await. When a caller invokes a callee, the caller doesn't actually transfer control to the callee, right? Instead, the caller receives a promise and resumes execution immediately, and the callee starts execution. And eventually, when the caller needs a result of the callee, so basically needs to coordinate, they need to coordinate their executions, then the caller awaits the promise. And if the promise is pending, the caller suspends until the callee terminates and completes the promise. Now, LFI, local, means we schedule this dialogue, we schedule this dialogue onto the local event loop, the event loop that happens in the process, right? The event loop that is present in Python. Whereas if we schedule it via an RFI, we schedule that promise onto the global event loop, right? And then the global event loop is responsible for handling handling the execution. So there are two event loops at play, depending on if you need to transcend the process boundary or not. So let's look at this one more time in detail, because we will see that come up when we look at the distributed protocol. Because interestingly, what Resonate relies on is a principle that is often called defunctionalization. So if you look at Wikipedia, defunctionalization, very common thing. It's basically everywhere where you have a function call, you replace that with a known command, so to say. And because of that, it's like where we have on a local process where we have a function call, globally we need to pass a message, right? So it's like here we can just do a callback locally, globally we need to send a message. So once we understand this flow, which is implemented both on the local event loop as well as the global event loop. Local event loop is just in memory and function callbacks. Global event loop, same flow, messages being passed back and forth. So this is independent, whether it's like local, you will find basically the same interaction in JavaScript, TypeScript, Python, but then also in Resonate's distributed async await. So you have a caller, and that caller basically creates a promise, right? And then the caller may await the promise. In that moment, the caller is blocked, right? So now the caller will not take another step until the promise is completed. Now, creating the promise basically invokes the callee, right? So now the callee kicks off and the callee executes. And when the callee terminates, the callee completes a promise. Now, when we are local, right, local event loop, for example, JavaScript, Python, you will experience that the creation and invocation is an atomic operation, right? So distributed system, nothing ever is atomic, right? So these are two separate ones. So it's beneficial to think about it in terms of creating a promise, and the creation of the promise kicks off the function execution. And then when the promise completes, right, the function execution the caller will then be resumed. Now, we can look at the distributed event loop protocol, which basically implements what we just said, not just within one process, but across processes. That's what Resonate actually did, right? We basically lift async await, the very same interaction, the very same concepts, functions, and promises, the very same interactions, we just lifted into the distributed world. The end. So our distributed event loop protocol basically consists of 3 different parts. The distributed coordination protocol, which is that dialogue of invoke, resume, yeah? And then the distributed recovery protocol, because one of the processes may crash, right? And then we need to reschedule that part of the async graph onto another node and repair the call graph. That is the distributed recovery protocol. And then we have a messaging protocol that we will get to in a moment. But first, I'd like to show where do these protocols even unfold, right? How should we think about the playing field? So, this diagram that represents the architecture of Resonate's implementation of the distributed async await runtime, right? And so there are 2 different viewpoints that we can consider. There's the physical view and the logical view. The physical view divides a deployment into the Resonate application nodes, sometimes referred to as app nodes, sometimes referred to as workers, and the Resonate server. So each process, each worker, whether it's a Node.js process or a Python process, right? And each of these is an instance of the Resonate SDK. And that acts as the interface between your user code, right? That's basically our kernel interface, so to say, the interface of your user code on the node and the Resonate server. So it's in these bubbles of execution to Resonate SDK, you basically see LFI, RFI, and await that thing, right? So and then the Resonate SDK drives the execution forward. So you can say that the nodes act kind of like as a data plane, right? The nodes are responsible for executing your function executions that are distributed across the system. And then the Resonate server acts as the control plane, right? The server durably stores the promises and then also coordinates between the function execution and recovers failed executions. And so then in that case, you can argue that the logical view divides deployment into application layer and the platform layer, right? So the distributed application and the distributed runtime. So that is delineated. Anything that says resonate here is basically the platform layer, right? So, and here you can already see that distributed aspect of the runtime, right? Because we have multiple instances of the Resonate SDK. And so yeah, the application layer represents the distributed application, consists of distributed function executions, and here like with the lambda symbol. And although the function executions are physically distributed across nodes, they basically form one continuous async call graph. And then we have the platform layer. This is the underlying distributed runtime. Right? And so every node is responsible for managing the remote function invocation and awaiting results. Right? And then when a function is invoked remotely, the SDK communicates with the Resonate server to manage the coordination across the nodes. And then the Resonate server coordinates function executions with the associated promises. Here with symbolized by pi. And the server coordinates execution and then also the potential recovery should something fail, all based on durable promises. So now let's look at the individual protocols. So first we have a messaging protocol. The entire system is based on message passing. We have message passing semantics. It's not connection oriented. It's not bidirectional. Right? So nothing has an inherent request-response relationship. Why? Because that makes for very flexible messaging infrastructure. You saw Kali basically just brought up the server and one of the workers. We have a very simple default implementation of that. That's basically just a long poll. Very simple default implementation. But this is a very flexible approach that supports your messaging infrastructure, right? You can, for example, whether you do it via HTTP calls, whether you do it via message queues, like for example NATS or AWS SQS, even in combination with very powerful frameworks like AWS Event Bridge and their routing subsystem. Since it's individual messages, once you're in possession of that message, do whatever you want with it, right? Until you basically route it to that worker that needs it. So very, very flexible, including how addressing works. So we basically have two types of addresses in the system. That's a unicast and an anycast. So unicast is a one-to-one relationship, right? So we have a sender and we have, if you have like here three potential targets, the unicast targets exactly one. So it's like from the sender to the receiver. More interesting, way more interesting is the anycast, right? With that, you can actually specify for your RFI, where should that message actually go, right? And with the anycast, you can, it's a one-to-one out of many relationship, a little bit like load balancing, right? You can specify, send it to one of these 2 out of 3 nodes in this situation. Now, interesting, very interesting is we have the possibility to say anycast, but prefer T1, which means if T1 is available, send it to T1. If it's not available, send it to anyone other in the group. That is so that we can implement something to the effect of like sticky sessions or sticky queues, right? We can send a message to the node that already has all of the information available that you need. But if that node crashed, take another node. You just basically then have to recover all of the executions that ran on that node. Now, the distributed coordination protocol basically sits on top of that message passing protocol, and that handles the coordination part, the invoke and resume part, right? And I need to fast forward a little bit because I see we're pushing up on time. So I jump across this little one, and I already present you with a final protocol that really shows each and every step. So here a caller, right, creates a durable promise via the server. That was the RFI that you see. So you create a durable promise via the server, and So then the server sends an invoke message, not in our case because it was a human in the loop, but sends an invoke message if you have to execute another function to another server via the anycast, right? So it's like, all right, it's like I have a durable promise, send it out, invoke message, work on that, right? And when the caller, the original caller, awaits the durable promise, we register a callback with the server, right? So now we have that situation where there is the caller sits there and waits on the durable promise, and somewhere else we have a function execution that is currently working on that promise. And of course you can do that recursively, right? There is no end to the recursion here. And however, we're not showing any recursion because already lots of messages. So it's like the caller sends, then it's like your code basically just returns, which means the SDK picks it up and then sends a complete promise to the server. And now all the server has to do is basically cycle through the promises. Through the callbacks and send the resume messages. And here you see the anycast with preference, right? We preferably send it to the server, to the worker that was already executing that, in case that one is still around, it's around, healthy and kicking, because there is a coroutine that just sits there waiting, right? So all we have to do is basically take that coroutine from memory, take the next step. However, if that node crashed in the meantime, no problem, right? It's an anycast with preference. We just send it to another node that is considered equivalent to this node. And from there on, then we have to recover the execution, basically re-execute the execution, and then take the next step. So that is the coordination protocol. The distributed coordination sits on top of two messages: invoke, resume, invoke, resume. And that's basically how you get the event loop. That's an infinity loop. So distributed coordination protocol, two messages. And the distributed coordination protocol sits on the distributed recovery protocol. And the distributed recovery protocol basically handles the crash recovery aspect of the thing. So the distributed recovery protocol is responsible for reliable message delivery and reliable message processing. So it has two phases, right? So it sends a task to one of the workers via your message passing network. Again, we have a default implementation that's built on long pole, but if you want to put it on a AWS message queue, process it via event bridge, and there via the event routing subsystem, you can do so, and eventually it will end up at one of the workers. Then the worker claims the task. That starts the reliable processing part. And that's nothing more than heart beating, right? So it's like at that point, after claiming it, the worker has to heartbeat the task. So I'm still working on it, still working on it, still working on it. And if it misses a heartbeat, right, then, not one, but if it misses heartbeats, then the server assumes that the worker has crashed and reschedules the task. And it is a task basically only contains two messages, invoke and resume, right? So and that triggers the reliable processing of the invoke message or the resume message on the worker side. And then as soon as the worker is done with creation, which basically means being done is either the execution has finished or the execution is blocked, once again, on something that's remote, right? You cannot make any more local progress. I'm done, I'm blocked. Yeah? Once it's blocked, it says, it tells the server, I'm done with that task. Server checks the task, and that particular message, the invoke or resume message, is now reliably processed. And these three protocols, the durable coordination protocol, invoke, resume, yeah, in combination with the durable recovery protocol, where we have claim a task and then heartbeat it, and then complete it, is the entirety of the distributed protocol of Resonate, and simply implements what is happening already in a local event loop, for example, in Node.js or in Python, and lifts it into the distributed world where we have to deal with coordination across machines and also the possibility of partial failure.
We have a question here from Luca. Asks, is the code that actually needs to be invoked also distributed?
If I understand that correctly, so first, Resonate, as it is today, does not deal with distribution itself or code deployment itself, right? So first off, once again, we made sure that this is very, very flexible. So we also do not have a hard-coded calling convention, but we have a default calling convention, right? How do you call something? And for Python, that's basically a combination of module name and function name, and then the arguments. And we encode that in a JSON document and store that in the durable promise. But you can completely override that. So if you have a specific calling convention, you can completely override that. So now the idea is that wherever you route the invoke message to, whatever node you route that invoke message to, or whatever human being you route that durable promise to, has to be able to correctly interpret that. So with our default implementation, right, it's like you basically have to deploy the code of your Python application to node A, node B, and node C, so that our server can send the invoke message, neatly wrapped up in the task, can send the invoke message to either of these nodes, and then the node executes that function. But again, the calling convention is up to you. But as of today, we do not deal with code deployment. So we are not trying, for example, to locally grab the transitive hull of your function call, try to pickle that or cloud pickle that and send it to another server. No, we don't do that. So we expect that wherever you route the invoke message or also the resume message, wherever you route the invoke message or resume message to, that node knows how to deal with that. And the default calling convention is basically what you would expect it to do. So if you call an RFI and you hand it like a remote function invocation, yet you hand it a pointer to a local function, it will then basically get the fully qualified name of that, put all the, serialize all the arguments, send it to the other node, look for the same function, buy the fully qualified name, get the function pointer, deserialize the arguments, call it. So it's fairly standard/default, so there's no surprise here, but it's up to you how to actually implement that. You can override that.
Lucas says, so just the function invocation details are distributed.
Yes, correct. That is entirely correct. Yeah. Again, you could also, if you are adventurous enough, you could actually go ahead, write your own calling convention, for example, with Cloud Pickle. I did not go down that road. I don't know how far you can take that. So you could actually store that in the durable promise itself. However, you will probably also eventually push up. I don't know how large Cloud Pickle payloads are, but eventually you probably also push the limits of the entire system if you always take the transitive hull of the code and send it somewhere else.
We have another question from Santiago. Asks, we've seen multiple tools, different approaches for durable executions. For instance, Restate has the concept of durable building blocks. Temporal uses jobs and tasks to perform durable executions. What do you think makes Resonate different to those approaches?
So what's super important for us is this focus on simplicity that guides all of our decisions. And one is, for example, you see that in the programming model. So we have only two core abstractions, and these two core abstractions are not our core abstractions. They are async await abstractions, functions and promises, right? And so, for example, we don't have signals and queries. So in Cully's download and summarize, when he walked us through it, we were not like calling functions and waiting on signals. We were invoking functions and receiving promises and awaiting these promises. And also the human in the loop step was not something extra. It was the same thing. It was once again a signal, right? And we do not have proprietary non-composable abstractions, right? It's not that we have a workflow and activity, and the workflow cannot really call other workflows. There is a child workflow relationship, which is different. There is a chain workflow relationship with it, which is different. Activities cannot call other workflows. Activities cannot call other activities. There is no, we don't have that. We only have functions and promises, and they compose recursively as far as you want. So one of our more demo-y or playgroundy implementations is an implementation of distributed factorial and asynchronous distributed Fibonacci. Never implement asynchronous distributed Fibonacci. That's just nuts, right? But it basically shows you can start anywhere. It's like Fibonacci 5 can be the workflow, and then Fibonacci 4 is the activity. But then Fibonacci 4 is the workflow, Fibonacci 3 is the activity, right? So this doesn't make sense. So we compose recursively from the largest systems to the smallest building blocks. It's all the same thing, right? Once again, it's like standing on the shoulder of giants. Async and await. Functions have been around since the 1960s, and promises have been around since the 1970s. We're not reinventing any of that. We're basically just reusing that. And it goes further than that, though. So we are also trying not only be simple on an API layer, right? You can argue, okay, they have two core abstractions, they compose indefinitely. That's pretty simple. But the underlying machinery must be ridiculously complex, right? While, of course, the underlying machinery is more complex than the API surfaces. Basically the definition of an API surface, right? That's why you have it. But as we still focus on the simplicity of that, right? So the distributed coordination protocol, 2 messages, invoke, resume, that takes care of the coordination, whether that is across 2 machines or across hundreds of machines. That is coordination primitive, right? And the distributed recovery is 4 messages, 2 individual messages, 1 request response pair. Yeah. So also very, very simple. So it's not only simple to use, it's also simple to understand, right? And the other one is there's a focus, because these primitives are so general. There's a focus on massive flexibility in there. So if you pick something randomly, like for example temporal, they dictate the deployment topology, right? You have the server in the middle, that's it, and then you have the workers around, star topology. The workers connect to the server. There's a long pole, the end, right? It's like we put a lot of time and effort in making this message passing protocol as brain dead as possible, right? So that you have a message. A message is basically an envelope. Write on the envelope whatever you want. Pass it to your messaging infrastructure. It can pass 100 hands. It can pass 1,000 hands, or it can just pass one, right? And you can still drive the entire system forward. So it's massively flexible, so that you can actually take advantage of the rest of your infrastructure. Like if you invest in AWS SQS and AWS Event Bridge, right? The Resonate programming model just plays nice with that. The same is true if you invest into Nuts.io and you say, hey, my entire communication backbone is Nuts, and they're, even if it's their request reply, we play nice with that, right? And yet the other thing is, but that's more of an approach situation or a philosophy situation. We also invest in like an open specification, right? We want this to be a heterogeneous landscape. So, for example, even our Resonate server is not a central component. One workflow can live across many different servers, right? So that a step can simply be, for example, another technology like Spark, like Apache Spark, Apache Workflow, Apache Airflow. As soon as you wrap that, so as you promisify that, it's like basically put the promise protocol in front of that, you can basically just spin up workflows where you just say await Spark job. Yeah? And also that protocol is dead simple. It's 4 messages: create promise, cancel promise if you don't want it anymore, resolve promise, and reject promise. Because only if the specification and the implementation is truly that simple do we actually have a chance of people implementing it. Right? So there's a lot of different dimensions where we think we are different. Obviously, it's like at the end of the day, it's in the eye of the beholder. So you tell us if that pans out. But yeah, that's at least our approach.
Awesome. Thanks, Brad. Appreciate that you think though.
Oh yeah, that's cool. Oh, I like it. Call it screenshot. Brilliantly simple, deceptively powerful. Love it.
Awesome. Well, we're definitely past time. What we planned, what we booked, and if there's no more questions, great questions, by the way. Thank you so much.
Thank you
for your interest and your participation. We genuinely appreciate it. We hope that you've gotten something out of this. And if you have any more interest, questions, please join the Discord. Come bug us. We are more than happy to spend time with y'all and dig into things more. The rest of our team, Tomas, David, Andres, they're always available as well. So yeah, thank you again very, very much. And we will obviously be doing more of these probably sometime in the new year, in January, maybe early February, we'll be doing another one. And if there's anybody else that wants to get involved, you start playing with Resonate and you've got something you want to cook up and show the community, let us know. Dominic, any final words?
Awesome. Hey, thank you very much. Thanks everybody for joining. Thank you, Kali, for the awesome demo. As Kali said, so it's like, obviously, if you want to chat, Resonate, join the Discord. But also, if you want to nerd out with me about like distributed system, also join the Discord. And then, yeah, with that, I'm very much looking forward to the next time. I hope everybody has a Merry Christmas, Happy Holidays, and then also a Happy New Year. And can't wait to see you all back in the new year. Cool. Thank you very much. Everyone has a good night.
Awesome.
Bye-bye.